Hey, welcome to day 4 of Unit 3. Today's lesson is rather short, but there's a lot of vocabulary involved. Fortunately, though, a lot of the vocabulary is sort of overlapping. So linear approximation and tangent line approximation are sort of mean the same thing. Let's see, I guess it would be easiest to just define them together. So linear approximation is a tangent line approximation. It's just a way of approximating a function using a line. It would be linear approximation. And tangent line approximation is using a line tangent to a curve. Okay, so using a line tangent to a curve to approximate values of the function. Okay, that's really the important one of the two here. Again, sort of pretty much mean the same thing. Linearization is sort of the process of finding a tangent line approximation. And typically when we say the local linearization of a function is represented as L of x. Okay, L of x, where L of x is equal to f prime of x naught times x minus x naught plus f of x naught. Okay, and all that is an equation for the line tangent to the curve at the point x naught comma f of x naught. Okay, at xy. Okay, where f prime of x naught is just the slope of the curve at that point. So all this gives us is a point slope form of a line that is tangent to a curve, and we use that line to approximate values really close to x naught. Okay, the value at x naught is equal to the function, but on either side of x naught it may be less than or greater than. Okay, there is an error which we'll get to in just a moment. So a differential is simply a small value. It's like a dx, a dt, a dy. All of those are called differentials. You know, we could use in the formula for area of a square, area is equal to s squared. We could use differentials to approximate errors in estimating the area. Okay. So the differentials involved here would be dA and ds. Okay. Relative error is going to come up when we start talking about using differentials to approximate error. Relative error is calculated by dividing the estimate over the actual. Okay, and that'll make more sense when we get to the example. The percent error is just a percentage. This represented as a percentage. So estimate over actual times 100. Okay, gives you a percentage. All right, so now that we have the vocabulary down, we can get to the meat of the lesson. All right, the examples. All right, so for the first example, we have how do we find the linearization of a function? Okay. So find the linearization L of x of some function f of x at a point x naught. So I give you the function, I give you the point. First thing we need to do is find the slope of the line at that point, the slope of the tangent line. So f prime of x equals 3x squared, and f prime of 2 is 12. Okay. So the linearization is 12 times x minus 2 plus the value of y at this point. So f of 2. So I also need to find f of 2, which in this case is 8. And that's it. Now, what is it? Here's f of x. I go over to 2. So this point is 2, 8. And all I've done is find the slope of the tangent line at that point and used the slope and the point to come up with the equation of a line. That's all the linearization is. So let's look at the second example here, part B. I need the derivative of f. I need the derivative at the point. And I'm also going to need the value of the function at that point, which in this case, right, the natural log of 1 is 0, I think, right? E to the what equals 1, 0. Okay. Just checking my work. So our linearization is 1 times x minus 1 plus 0. Okay. Just to clean that up, simply x minus 1. Great. Now what do these linearizations do for us? Well, they let me approximate values of the function really, really close to 2 in this case and to 1 in this case. So let's see, what if I wanted to know or approximate f of 2.1? Well, I can use the linearization to approximate it. So L of 2.1 is 12 times 2.1 minus 2 plus 8. 2.1 minus 2 is 0.1. So I have a tenth of 12, which is 1.2 plus 8 is 9.2. Okay, and I believe if you plug in 2.1 to the original function, 2.1 cubed is somewhere in the ballpark of 9.1 something. Or no, it should be more. I think it's like 9.3, something like that. So that's what we're doing. We're finding a function, a simple function to solve that approximates something that's more difficult to solve. Obviously, these two examples aren't that difficult, but the functions could be pretty intense, and our local linearization would give us good estimates of the function at the point of linearization. All right, so for the last example, we're going to be using differentials to estimate error. So let's say we have a circle, and we know that it has a radius of 24 centimeters. But it's also known that there is a maximum error in measurement of 0.2 centimeters. So that's like saying the radius of this circle is 24 centimeters plus or minus 0.2. We're not sure. It could be 24.2, it could be 23.8. It's in there. It's in that ballpark. But we say it's 24 centimeters with a maximum error in measurement of 0.2 centimeters. Okay. We're going to use differentials to estimate the maximum error of calculated area. Okay. So the formula for area is pi r squared. And so what we'll do now is differentiate this with respect to r. Okay. So dA over dr equals 2 pi r. Okay. So what I'm looking for is how much the area could change with respect to this change in the radius. So how is that going to be affected? Okay. So dA is 2 pi r dr. Okay. And so then solving for dA, by plugging in all of our values, we get 2 times the radius was 24, and the difference in the radius is a maximum of 0.2. So the maximum error in the area is about 9.6 centimeters. Okay. So if we calculated the area of this disk with the measurement of 24 centimeters for the radius, knowing that that measurement could be off by 0.2 centimeters, we could estimate that our measurement of the area could be off by about 9.6 centimeters. Okay, so that would be our maximum possible area, or error in measuring the area. So then the next part of this question asks us for the relative error. Okay, so we said the relative error was the estimate over the actual. So that's our maximum error divided by the actual area. If we used 24, is, I think it's, I forgot my pi, is 9.6. I think it's 576 pi. Okay, and that, I just got that by using 24 and finding the area. So what should the area be? The area should be 576 pi with a total maximum error of 9.6 pi for a grand total of 0.0167. Okay, so that would be my relative error, which is fairly low. Okay, what's the percent error? We just multiply the relative error by 100 to get a percent error of 1.67. Okay, so in calculating the area of this disk with a given radius, knowing that our measurement could be off by about 0.2 centimeters, we expect a 1.67% error in our calculation of the area of the disk.